Hello and welcome to a problem-solving session on the concept of electric fields. Um, Before we get going on here, I just kind of like to keep score of ideas that we have for solving these problems. So previously, we built the concept of Coulomb's law, and that says that an electric force between two charged objects is equal to the Coulomb constant times the magnitude of the first charge times the magnitude of the second charge divided by the distance between them squared. And that, in addition to the things we knew from Physics 1, was pretty much all we used to solve the first set of problems with electric forces. Now we're introducing the concept of an electric field and saying that the electric field at a certain point is equal to the force on some charge at that point divided by the magnitude of the charge itself. And so because of that, we can plug this force equation into the numerator there and deduce a formula for the electric field from a point charge, which is kq over r squared. So one distinct difference is when you're talking about an electric force, you have to have two charges. When you're talking about an electric field, you only need one charge producing that. And I actually should not have thrown the vector sign up there unless I somehow are specifying the direction over here. So let's just put more symbols on to fix that. All right, there we go. So those are the basics that we're going to need to attack this problem set, in addition to a couple of things that you should have carried over from Physics 1. So we will take a look at the first problem here. First problem says the figure shows two charged particles on an x-axis. We have negative q, which has a charge of negative 3.2 times 10 to the negative 19 coulombs at the minus 3 meter mark, and positive q, which has a charge of plus 3.2 times 10 to the negative 19 coulombs at the positive 3 meter mark. What are the magnitude and direction relative to the positive direction of the x-axis of the net electric field produced at point P, which is up here 4 meters up along the y-axis. I think it's very helpful to draw a diagram on this particular situation, so let's go ahead and do that. Do I get an electric field contribution from the negative q charge? And the answer is yes. At point P, that electric field is going to point back towards the negative q charge, and I don't know how long we want to draw that. I'm just going to draw it an arbitrary length and label that that is the electric field from the negative charge right there. Similarly, the positive charge is going to produce an electric field at point P, but it's going to point away. If you have to figure out the direction of electric field, a good trick is to just imagine putting something positively charged here at point P and letting it go. It would fly away from this positive charge. So the electric field here is in the upward direction. And because these things have the same amount of charge as each other, and they're the same distance away from point P, these two electric fields are the same size as each other. And that's going to be handy because it'll cut down on the number of calculations that we need to do. And then the net electric field, if I add those two vectors together, I'm going to use the little parallelogram method for working out what that resultant electric field would be. The net electric field points over to the left, directly to the left, in fact. And if we think about our strategy, in order to figure out how big that one is, we're going to figure out how big one of these electric field vectors are. We're going to then figure out how big its horizontal component is, because only the horizontal components of these two vectors are going to add to each other. The two vertical components cancel each other out. So once we figure out how big one of these is and figure out how big its horizontal component is, the last step will be then to double it, because the net electric field is produced by both of these electric field vectors. All right, so these are considered point charges, and that means that we can calculate the electric field using the electric field relationship for point charges. The Coulomb constant times the charge over the distance from the point where you want to calculate the electric field squared. Well, that means the electric field, let's just say we'll do the positive one, is 8.99 times 10 to the ninth Newton meters squared per Coulomb squared. That's the Coulomb constant. The amount of charge is 3.2 times 10 to the negative 19 coulombs. And we need the distance away, so we need to do a little bit of distance work on our diagram here. We're told that this distance right here is 3 meters. We're also told that this distance right here is 4 meters. But we need to know what this distance is right here. Recall from your previous geometry work that a squared plus b squared equals c squared. So 3 squared is 9. 4 squared is 16. 9 and 16 together are 25. And the square root of 25 is 5 meters. You might have even remembered that quote-unquote special 3, 4, 5 triangle from previous math that you've done. So I'm going to have 5 meters in the denominator. Make sure I square that. And if I punch all those numbers into my calculator, I get 1.15 times 10 to the negative 10 newtons per coulomb. How do we get those units? Well, a coulomb here is going to cancel one of the coulombs here. Meters squared is going to cancel meters squared here, and we're left with newtons per coulomb. Electric field, after all, tells us how big the force per some amount of charge is at a location in space. So that's step one. Now I want to figure out the electric field from the positive charge, but I just want to figure out what the x component of it is, because the two x components add. If you break that positive charge's electric field vector into x and y components, the two x components are going to add, the two y components are going to cancel. So to figure out the x component of anything, you need to know what this angle is right here, but that's the same angle that I have back here. And I need the cosine of it. So the x component is going to be the overall electric field from the positive charge times the cosine of whatever that angle is. Well, let's work out what that cosine is. Recall again from previous trig work that the cosine of any angle is the ratio of the adjacent side to the hypotenuse. So here, the adjacent side is 3, and the hypotenuse is 5. And you literally can plug in 3 over 5 and figure out what theta is, and then go back and plug theta in here. But the cosine of theta is just 3 over 5 in this case, so that's a little bit less work to do. 1.15 times 10 to the negative 10 newtons per coulomb. That's the magnitude of the electric field overall from that positive charge, times 3 over 5. That's the cosine of the angle of that particular triangle, yields an electric field of 6.9 times 10 to the negative 11 newtons per coulomb. And the final step is, that's one of the x components. The other x component needs to be added to it, but it's the exact same size. So the net electric field, which is the x component from the positive, the electric field due to the positive charge, plus the x component from the electric field due to the negative charge, is just going to end up being 2 times our previous result. And that is 1.38 times 10 to the negative 10. Still has units of newtons per coulomb. How do we specify the direction? Well, it's directly to the left. So you can say in the negative x direction, but most commonly, especially if you do these in Mastering Physics, it's looking for an angle. So if the positive x direction is 0 degrees, I have to rotate by 180 degrees once I'm pointing in the negative x direction. So I'm going to specify the direction as an angle here. And actually, it doesn't matter. 180 degrees is either plus or minus 180 degrees. You can go either way around the axis. All right, problem 2 in this problem set is kind of a similar setup. In the figure, the 4 particles are fixed in place and have charges of, let's see, Q1 and Q2 are each 5e, Q3 is 3e, and Q4 is minus 12e. If you've not seen E before, E is the fundamental electric charge. It's the charge on one electron. It's 1.6 times 10 to the negative 19 coulombs. And we'll go ahead and plug that in if and when we need it. If you're thinking ahead, any of those kinds of numbers you might need on an exam will be provided on the exam in terms of constants and values of fundamental masses and fundamental charges. The distance d in this case is 5 micrometers in all of those d's labeled up in my diagram. And what is the magnitude of the net electric field at point P due to the particles? Well, I'm going to just isolate and redraw point P over here and use what I know about electric fields to sketch individual field vectors for each of those points that we have here and see what we come up with. Okay, so let's take them one at a time. This is again called the principle of superposition if you use that language in Physics 1. Basically it says, let's ignore 3 of the 4 charges. Let's work out what the electric field is from charge 1. Then let's ignore a different 3 charges and just work out what the electric field is from charge 2 and keep following that pattern. And once you've worked out what the individual electric fields are from every point charge, you can sum them all together. All right. So the electric field at point P due to charge 1, well, charge 1 is positive, 5e. So the electric field is going to be pointing away from the line between charge 1 and point P. And because it's the first vector I'm drawing, I get to draw it exactly whatever length I want to. So this is the electric field from charge 1. How about the electric field from charge 2? Well, charge 2 is also 5e worth of charge. It's also d away, but it's on the other side of point P. So the electric field contribution from charge 2 is going to be something like that, and I don't know if I did those exactly the same, but the intent was to draw those 2 vectors the same length as one another. So one thing you might notice right away is those 2 vectors are going to cancel each other out, and that's going to reduce the amount of work we have to do in calculating any sort of net electric field at point P. Let's move on to charge 3. Charge 3 has a charge of plus 3e, and it's a distance d away. So I would draw its electric field vector pointing, again, away from the line between wherever charge 3 is and point P, but I'm going to try to draw it 60% of the length of the electric fields from charge 1 and charge 2. Why is that? Well, the electric field for any point charge is equal to K times Q over R squared. So if I've got 3e instead of 5e, it's going to be 3/5 of what the previous electric field was. All right, and finally, we've got a minus 12e up here. So if we ignore all the other charges, the electric field due to this negative charge is actually going to point toward the 12e. How big is it going to be? Well, the electric field from the 3e charge would be K times 3e over d squared. The electric field from the 12e charge, just magnitude, I'm not worried about direction, I've already taken care of that by thinking about the situation, is K times 12e, and now it's a distance of 2d away from point P, 2d squared. That works out to be K times 12e over 4d squared. And notice something interesting. 12 over 4 here that can be rewritten as K times 3e over d squared. And lo and behold, those are the exact same ratios. So I've got 4 times as much charge, but it's twice the distance away. And so the effect that the Q4 has at point P is the exact same as the effect that Q3 does in the opposite direction. And there we go. And welcome to one of the easier problems to answer, because the net electric field at point P, if you add all of those vectors together, is 0. Now, that's indeed a very special case. If I shifted even slightly in the direction of one of these charges, that would no longer be 0, and I'd have to work out all the individual vectors and sum them. All right, our third problem on this problem set involves an alpha particle. It reads an alpha particle, which is the nucleus of a helium atom for you chemistry fans out there, has a mass of 6.64 times 10 to the negative 27 kilograms and a charge of plus 2e. Again, there's that e, that's the fundamental charge. Because it has 2 protons, and the protons are equal in charge to an electron, then that's why the charge is 2e for an alpha particle. What are the magnitude and direction of the electric field that will balance the gravitational force on the particle? All right, totally don't need to, but lots of us get into physics problem solving because we like to doodle. So I'm going to draw my little, all right, I got a proton, and I have a neutron and a neutron. So this is my little sketch of my alpha particle. An alpha particle is made up of 2 protons and 2 neutrons, and indeed is the nucleus of a helium atom. Alpha particles also are one of the kinds of radiation given off by more unstable nuclei that are further down on the periodic table, and one of the forms of radioactivity, though we will not be studying that phenomena in this course. Okay, so if I just stick an alpha particle out there in space, it's got some mass, not a huge amount compared to what we have, but it has some mass, and that means it's going to have a gravitational force on it. And we want to balance the gravitational force on the particle. So if I don't want this particle to fall, I need to put an electrical force on it, and the electrical force has to go in the upward direction. And that electrical force is going to be produced by an electric field. And so if this electrical force is upward, there must be an electric field in this area that's also upward. So I'm just going to draw a series of field lines to indicate our electric field. Again, not necessarily information we need to solve the problem, but who doesn't like to draw colorful lines when they're doing problem solving? All right, so I have a uniform electric field. It's up. Positive particles get pushed in the direction of electric fields. Negative particles get pushed opposite to the direction. So if this were some negative particle that I was trying to balance the electrical and gravitational forces on, the electric field would need to be in the downward direction. All right, so let's go back and use some Physics 1 here. We know from Physics 1 that the sum of all the forces on an object is equal to the mass of the object times the acceleration of the object, but we want to balance, which is code for we want these to produce no acceleration. What does that mean? It means that the electrical force needs to balance the gravitational force. Gravitational force we're familiar with from Physics 1. That's mass times g. Again, g is often called the acceleration due to gravity. A better name for it would be the local strength of Earth's gravitational field here. It's how much gravity is pulling on this particle, given where it's located. And to get the electric force, what I do is I take my definition of electric field. Electric field is defined as the force on some test charge divided by the magnitude of that test charge. Well, if I move this Q up to the other side, I'll have an expression for an electrical force on a charge. And an electrical force on a charge is equal to the strength of that charge times the strength of the electric field that it's sitting in. All right, we've almost got what we need. We want to find the magnitude of the electric field, that's E. So algebraically, we would move Q to the other side. I've got mg over Q. The mass, the problem tells us, of the alpha particle is 6.64 times 10 to the minus 27 kilograms. You chemists out there might recognize that as 4 AMUs. G is 9.8 or 9.81, whichever you prefer. I'm going to use newtons per kilogram because it's going to leave me with standard units for electric field. A newton is a kilogram meter per second squared, so if I cancel out the kilograms, this is the same as 9.8 meters per second squared. And the amount of charge, well, it has 2e, and so that's 2 times the charge of an electron. You can Google that, or maybe you have it memorized. It's 1.6 times 10 to the negative 19 coulombs. Again, if you needed to know that on an exam, that number would be given to you. And if you plug all those into your calculator, you get 2.03 times 10 to the negative 7. Units are, let's see, kilogram cancels kilogram. I'm left with newtons per coulomb, which is the standard unit for an electric field. And what's the direction of the electric field? Well, we already answered that. If I have an upward electrical force and the particle itself is positively charged, that's consistent with an upward electric field as well. Or if you were doing it angle-wise, the standard angle of 0 to the right, this would be a 90-degree angle for that problem. Finally, another problem that illustrates putting together these new electrical ideas with things you learned back in Physics 1. Sorry for those of you that hated Physics 1. Got to keep using those ideas as we move forward here. An electron is released from rest in a uniform electric field of magnitude 2 times 10 to the 4th newtons per coulomb. Calculate the acceleration of the electron. Ignore gravitation. How long would it take for the electron to reach the speed of sound? And how long would it take for the electron to reach the speed of light? And the parenthetical notes that this isn't exactly kosher physics, because when you get near the speed of light, there actually is a different set of rules called the theory of relativity that governs how things behave. All right, so I have an electron, and if I put it in a uniform electric field, which again we could sketch by a series of parallel field lines. Let's remind ourselves that's an electric field. This electron is going to naturally actually move against the electric field. Negative charges move against that. We don't need to know that to solve the problem, but if you let that electron go, it would fly to the left in this situation. We want to know the acceleration of the electron. Well, acceleration, that's back to Physics 1. So we first took and defined at least average acceleration as a change in velocity over a change in time. But I don't know how much velocity change I had or how much time went by, so that's not going to work. We had a bunch of kinematic equations where we saw acceleration show up, but they were all derived off of this definition and the definition of average velocity. The next place we ran into average acceleration, though, was Newton's second law, which said that the net force on an object is equal to the mass of the object times the acceleration of the object. And this seems promising because we know the mass, or we can find the mass, and we're going to be able to know the force, too, using a similar kind of process we used in problem 3. So let's go with this, and I'm just going to strike the vector signs and say that the acceleration is equal to the net force divided by the mass. Well, what kind of forces are exerting influence on this negative charge? Well, there's a force from the electric field, so we could go ahead and label this arrow as a force from the electric field. It's, again, to the left, opposite to the direction of the electric field because the particle is negative. Problem tells us to ignore gravitation, so we don't have any gravitational force here. And that's pretty common when you're doing particle physics. These end up being really, really, really tiny forces. And in fact, That's it then, the electric force on here. There's no other objects in this system to exert a force on that electron. So that means the acceleration is actually the electrical force divided by the mass. And we saw previously you can rewrite the electrical force as the charge times the strength of the electric field. And again, that's divided by the mass. So let's plug stuff in. The charge of an electron is 1.6 times 10 to the negative 19 coulombs. The electric field, the problem tells us, is 2 times 10 to the 4th newtons per coulomb. And the mass, again, you can look this up, but the mass of an electron is believed to be close to 9.11 times 10 to the minus 31 kilograms. And if you punch all of those numbers out, you get an acceleration that is 3.51 times 10 to the 15th meters per second squared. It's an enormously high acceleration. It's not super strong electric field, but you have a tiny charged particle that you're putting in it, and it receives an enormous acceleration. Doesn't mean this is ridiculous and we should toss this out. It just means it's very unlikely that this electron is going to accelerate for any appreciable fraction of a second, because this is saying if you accelerated for 1 second, you'd be moving at a speed of 3.5 times 10 to the 15th meters per second. That's 3.5, I think, quadrillion meters per second, way past the speed of light, and broken all kinds of laws of physics. So that's A. B asks us, how long would it take the electron to reach the speed of light? And here's where we want to use the definition of acceleration that we had from Physics 1. If acceleration is a change in velocity over a change in time, then we can write that a time interval is a change in velocity over an acceleration. Well, the speed of sound, you may have studied this in Physics 1, may have not. It depends on a lot of things. It depends on the atmospheric conditions, it depends on the temperature, all kinds of stuff. So it's usually somewhere in the 330 to 350 meters per second range. Different textbooks list different values as quote-unquote standard. I'm just going to use 340, which is intermediate there. So that means the time interval would be the change in velocity. Well, I've gone from 0 to 340 meters a second at a pedestrian acceleration of 3.51 times 10 to the 15th meters per second squared, and that works out to be 9.7 times 10 to the minus 14 seconds, an extremely short window of time there. If you do a similar calculation for light, you need to know that the speed of light is about 3 times 10 to the 8th meters per second. So the new time window then would be 3 times 10 to the 8th meters per second divided by same acceleration, 3.51 times 10 to the 15th meters per second squared, and that works out to be 8.5 times 10 to the minus 8 seconds. Still a really short window of time, but one that actually might have a chance of being experimentally measured. Again, the problem with this one is getting up to this speed. Once you get up close to this speed, the rules of physics change on you, and Newtonian mechanics no longer apply. All right, so there you have it. Those were our solutions in class for the 4 problems we did about electric fields. As always, let me know if you have questions, and if you notice an error in the solutions, I would love for you to point that out to me. Thank you.